So in this lecture, we're going to keep going with molecular geometry. And I now have my models. I've got a tetrahedron with green dots, another tetrahedron, a few that we can kind of play with, and then got an octahedron, which is useful because if you pull off the top and bottom, you can see that example where the one depiction of methane might not give you the best separation of atoms. So I'll kind of bounce back and forth between sharing my screen with you and kind of, yeah. Okay, so we were talking about drawing tetrahedrons last time, and again, the tips are tips for drawing a tetrahedron are you want two straight lines and you want them to be bent, and they could be in any direction. So again, that's kind of my go-to. You could have the straight lines this way, so long as they're bent from each other. If you just draw them linear, that's not going to get you there. So I've got top, let's go bottom, and sure, side to side. And so in all of these, we could kind of think about fitting three things around our carbon atom, where if we go here, 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 we kind of divide the space between the carbon and its, excuse me, and its adjoining groups with kind of into thirds. Now that helps guide our eye as to where the wedges and dashes are going to be. They're going to split the space between the two hydrogens. In this case, we're using hydrogens. It could be anything. They are going to split, the wedge is going to split the space between those two lines. And then what we do is we just add a dash sort of offset from the wedge. The wedge is more important. The dash just kind of fits in there. We know that in reality, the wedge and the dash are directly on top of each other. So that's sort of me drawing a tetrahedron. Let's actually go ahead and pull one up in front of the camera. Okay, so tetrahedron, the black dot is supposed to be carbon. Now let's try to, there's a few ways that you can depict this, but I'm going to, gosh, this is like way harder than with a document projector. Okay, in my mind, I've got one atom and another atom that are directly in plane, one that's sort of coming out towards you. This would be my wedged atom, and then you can kind of see back behind it, almost perfectly overlaps, so we just tilt it a little bit, is our wedged, excuse me, our dashed atom, which is right here. So this is going to be our dashed atom, wedged atom, line, and line. So that sort of depiction will get you there quite quickly. So, whereas if we have all of the atoms like this, kind of forming this square planar arrangement, you don't get as much separation between these two atoms as you do in the tetrahedron, where neighboring atoms are now split a little bit further apart at 109.5 degrees. So, other geometries to be mindful of or to know. We have pyramidal, bent, trigonal planar, and linear, all in addition to tetrahedrons. So we have sort of, looks like 5 geometries that we need to know. What's interesting about this is students often struggle with this just because they report back that there's some brute force memorizing that's involved to get to know all, I guess I'm looking at this now, 5 different geometries, again, tetrahedral in addition to these other 4. But the thing to note is that pyramidal and bent are based off of the tetrahedral geometry. Okay, let's look at that. Clean this up. Okay, they're all based off of the tetrahedral geometry. So going on to the next page, what we want to look at is our first example of a, and did I do this right? Yeah, pyramidal, yep, and bent. Okay, so the first example I want to look at is the trigonal planar molecular geometry. Molecular geometry. Okay, so a good example of this is NH3, which is the nitrogen variant of water. This is called ammonia. So ammonia, you could think about the Kekulé structure like this, where we have 3 hydrogen atoms around the nitrogen, all connected by covalent bonds with 1 lone pair of electrons that nitrogen gets to keep along, that nitrogen gets to pick up as part of just being nitrogen. And with all of that together, we have 8 electrons for an octet. Now, what I want you to notice is that the nitrogen has a few things to note here. 4 things. Okay, 4. If I see 4 things around any central atom, I know that I want to arrange them in a tetrahedron. So I'm going to write here, we're going to have a tetrahedral arrangement of its things. Now, I'm not sure how my colleagues that are also chemistry educators think about the word things, but it's been a very useful word for me, especially as we get into something called hybridization. So things are going to be lone pairs and other atoms. I wish I could flip these. Maybe I can. Let's just do that. It's going to make this easier. Okay. Oop. That failed miserably. Okay. Let's try that again. So these are going to be other atoms that are bonded by covalent bonds and lone pairs. Now, it's important to note that with lone pairs, these things count as one thing. So if you have a lone pair, you have one thing attached. So what I'm saying is we've got 1 with this lone pair, 2 with this hydrogen, 3 with this hydrogen, and 4 with this hydrogen. 4 things. So we're going to have a tetrahedral arrangement. Now you notice that I also used the word arrangement here. I really like that word. Now it's a tetrahedral arrangement, not a tetrahedral geometry. Now why is that? Well, let's look at that central nitrogen atom. Okay, so we've got a nitrogen, and if we have a tetrahedral arrangement, that means we're going to have 2 straight lines that are in plane, sort of offset of each other in a bent, sort of not linear. Bent is the word to use, so I'll just call it bent. Okay, then we've got a wedge and a dash. What we need to do is occupy these 4 sites around the nitrogen atom with the various groups. I'm going to pick, for the sake of discussion, to put the lone pair of electrons, one of its 4 things, at the top position. Hydrogen going down and to the right, hydrogen going down to the left as a wedge, down and to the left as a dash. Okay. What I want us to remember is that electrons don't count toward geometry. So the electrons do not count when you're looking at or assigning the geometry. Yes, it's true that this is a tetrahedral arrangement, and for the sake of this discussion, these are separated by 109.5 degrees, a little bit bigger, like a hair bigger, because it's an electron. It's a sort of naked electron that's not bonded to something else, repelling things a little bit further. But anyway, the 2 things are separated by 109.5, just like any other tetrahedral, let's say. But the thing is, electrons don't count towards geometry, because when we try to visualize these things, we actually crash particles into the nucleus to get us some idea of what the geometry actually looks like. Okay, so we're going to crash particles into the nuclei of the atoms that make up ammonia. And what that means is that we're not going to see the electrons. So this is going to look exactly like methane, except it's been decapitated. All right, this looks exactly like methane, except boop, I'm just going to chop the top of it off. Now, it's a little bit hard to see, but when you do that, to squint a little bit. But when you do that, if you look at the model, it turns out that the bottom, this is kind of like a pyramid. This looks like a pyramid, right? I mean, it's a really short pyramid. I know, it's a molecule, come on. But the bottom of it forms a triangle across the 3 white atoms that we can actually see. And if you look at this, the way the black atom is depicted, it kind of looks like it's raising up to be the tip of a pyramid. So we say that this now has a pyramidal geometry. And sometimes people call it a trigonal pyramidal. I prefer just to call it a pyramidal to remind myself that it's just a pyramidal, or it's just kind of like a pyramid. So this is our pyramidal geometry. It's a tetrahedral arrangement of 4 things, but one of those things is a lone pair of electrons, which we can't see. You cut off the top of methane, it looks like just a pyramid. So we're going to call it a pyramidal geometry. Okay, let's go on to the next geometry. The next geometry is going to be bent. We already looked at the bent molecular geometry last time when we were looking at water. So let's pick on water again, H2O. So if we draw a Kekulé structure of water, we have an oxygen as a central atom, 2 lone pairs of electrons, and 2 bonds to hydrogen atoms. Go ahead and count the number of things around that central oxygen atom. I'll let you pause the video. Maybe I'll just keep making typos. How many things around that central oxygen? Okay, so if we look at this, around the central oxygen, when we're thinking about things, the answer in this case is we have 1 for hydrogen, 2 for hydrogen, 3 for one of the lone pairs, 4 for another lone pair. Remember, it's the pair of electrons that counts as one thing, not each separate electron by itself, not yes or no to having a lone pair of electrons. Each of the pairs counts as separate things. So how many things are around the central atom? We have, cancel. We have 4 things around the central atom. What this means is that these 4 things are going to be arranged like a tetrahedron. Okay, so we're going to have these 4 things arranged as in a tetrahedron. Let's go ahead. In this case, I'm going to, and you could do this with anything, you get the exact same thing, but I'm going to put the lines, the hydrogens attached to the lines, and my wedge is going to go to 2 dots, and my dash is going to go to 2 dots. Okay, now just like before, when we crash particles into our molecule to try to get an idea of what the geometry looks like, we can't visualize or see the electrons that are attached. Even though they're attached in a tetrahedral arrangement, we can't see those. Instead, all that we see is this grouping of 3 atoms. Now, these 3 atoms are in a plane. Okay? There's no 3-dimensional component to them. They're in a plane. Right? Are they a straight line? No, I mean, I know 3 points can make a line, except when one of those points is like way offset, right? 3 points define a plane, 2 points define a line. 3 points can define or be part of a line if, you know, they fit y equals mx plus b. So they define a plane, not a straight line. It's not a straight line, but it is a plane. We would say it's a bent line. Okay, so what I'm saying is when we have a central atom with 4 things attached to it, and 2 of those things are lone pairs that can't be visualized, we're going to have a bent geometry. That allows us to spread everything out, 109.5. I mean, I'm going to write 109.5 because that's the number you need to know to like get employment in the chemical sector. But in reality, it's a little bit tighter because lone pairs push on the other atoms a little bit harder. So it's a little bit more narrow between the actual two atoms. But between an atom and a lone pair, will be a little bit further. It'll all average to about 109.5 when everything's said and done. It's a tetrahedral arrangement. It's a really good way to position yourself so you have maximum spread of electrons that aren't paired up, that are beyond pairs, okay? So one lone pair, they're happy to sit together, that's those two electrons, but they want to be as far away from the other lone pairs as possible. Okay, so what we're left with is a little chart of molecular geometry, where what we could say is we have the number of groups, and let's even use that word, things. Okay, and in every case here, this is going to be 4. And then what we would say is the arrangement at the central atom in every case is going to be a tetrahedron. Okay, but what differs in each case is the number of lone pairs. We could go from 0 to 1 to 2, and that's going to control our geometry. So the geometry for having 0 lone pairs in a tetrahedral arrangement is a tetrahedron. We have a tetrahedral arrangement of things, all of which can be seen, all of which are atoms. So we have a tetrahedral. And I don't even, to be honest, I'm not sure if it matters whether we use tetrahedron or tetrahedral. Both are fine in my book. There's certainly a reason to use one or the other, but it's never been important to me. Okay, so if we have one lone pair, that means we can't see one part of it. That's like decapitating the molecule, so that's pyramidal. If we have 2 lone pairs, that's bent. Now we can only see part of it. Now, this is a nice chart to know, I guess. The point of it, and the point of this lecture, is to kind of bring us all back to recognizing that even though there are multiple geometries, 5 in total, I think I said, that we have to memorize, 3 of which are defined by a tetrahedral, okay? A tetrahedral arrangement. Because most of the time, many times you'll have 4 things attached to an atom. That's how you get to 8 electrons total, is you attach 4 things by way of 2 electron connections, be them bonds or lone pairs of electrons. Okay, one thing I want to finish on, I won't even make a separate sheet of paper. I'm just going to stop sharing my screen, is you might be like, okay, well, what if for the pyramidal geometry, okay, tetrahedron is a tetrahedron. So if you have it like this, or like this, or like this, or like this, I could draw different straight lines, wedges, and dashes. But what if instead of pulling off the top, what if I pull off the side of the molecule? That is, I'm going to put a lone pair of electrons at this connection point in my at the central atom of my molecule. Is it still pyramidal? You didn't take off the top, you didn't decapitate the thing to make it look like a pyramid. But remember, everything can roll around in 3 dimensions of the universe. So I'm just going to roll it this way, and I get back to my pyramidal geometry. So it always works. Removing one thing gets us to a pyramidal. Moving another thing gets us to a bent structure. Now you might be like, well, I'm going to take off the 2 lines and leave behind the wedge and the dash. Okay, so you have a structure like this. I remove the top, the 2 kind of planar lines from my depiction. Again, you can just roll these things around and get back to straight lines in this depiction. So molecules can roll just by kind of changing how they rotate and roll in 3 dimensions. You change what happens, which one is designated as a wedge or a dash. Okay, so hopefully that was somewhat clear. What I'm saying, maybe I'll just kind of go through it super quick on a new page, is molecules can roll. What I'm saying here is don't get too tied down to what is your wedge in your dash. Let's say I've got a molecule that looks like this, where I replace one of the hydrogens with a chlorine atom. I'm just going to let that molecule kind of roll around. Let's push it down on its side, push it down this way. If I do that, I'm going to put the chlorine here. Then there's going to be an H here, an H here, and an H here. If I kind of flip it around, if I flip it around this way, I can make the chlorine now a wedge. There's still one hydrogen that's a dash, hydrogens here and there. You could even kind of tip it sideways a little bit. If I tip it sideways, let's make this interesting. Just kind of tilt it sideways. I can get to here. Now, there's no way you're following all of these rotations. It's unlikely, let me say it this way. It's unlikely that you're following all of these rotations and rolls and tilts and flips in your mind. Just suffice it to say the molecule is not changing when we roll it around in space. We just pick one way to draw it. And so there's many possible ways to draw these molecules with wedges and dashes. Yours could have had the wedges and dashes flipped a different way, just up and to the right maybe. As long as they're right next to each other and there's two straight lines, we're good. We're all drawing the same thing. It's just rotating around in the three-dimensional universe. Okay, so I'm going to really stop now. In the next video, we're going to look at what happens to the orbitals to allow for this sort of arrangement of atoms in three-dimensional space.